Today I'm going to give you a brief overview of measuring dissolved oxygen in a brewery, kind of looking at things from maybe a 30,000-foot view and then drilling in occasionally down. But what we want to do here is just kind of go over an overview. What is dissolved oxygen in a brewery? Why are we measuring it? And how do you measure it? So what we're going to do is go through a few different slides here, starting with why measure O2. We'll talk a little bit about different oxygen measurement technologies. We'll talk about wort O2, process O2, package air, and then package O2 and TPO and what it all means and how those things all relate to each other. Really, the question about why measuring O2 comes down to O2 reacts with beer. And O2 can react with beer really quickly or really slowly, depending upon the storage conditions, the temperature, the type of beer, whether there's yeast around. So if you look at this graph, what you see is a decay over time, but note that there aren't any units in the x-axis. And the reason that I didn't put any units there was that time could be minutes, it could be hours, it could be days. It's probably not going to be seconds, and it's not going to be weeks, but you're definitely looking at time where O2 will deteriorate really slowly in the beer. And I think it's also important to note that the flavor changes won't show up probably for another maybe 2 to 3 months, unless it's heavily oxidized, in which case they could be showing up after 30 to 45 days. Dissolved oxygen theory really is what drives how we measure oxygen. And the reason I want to go through theory here is because I think it's really important to understand a little bit about the background of the theory before we go and we really look closely at how the instruments work and what it is that we're measuring. So oxygen sensors all measure the partial pressure of a gas. What that really means is that they're measuring the percent O2. So if it's a package with high O2, they're going to be measuring the percent, or low O2, they're going to be measuring a different percentage. Why that's important is solubility of oxygen in different types of liquid changes. So we have to take that percent O2 and apply a solubility factor, and then we take that value and we look at it in terms of a weight per volume type of a unit. So it's going to be milligrams per liter, which would be also called parts per million, or micrograms per liter, which would be called parts per billion. To take a little bit of the theory and talk about solubility and also start to apply it to the brewing process, I want to just show a graph here. And this is a graph showing air, so 80% nitrogen, 20% oxygen, and what happens, how much of it the different gases dissolve into liquid. So if we take our gas component that's 80% nitrogen and 20% oxygen, and we dissolve it in the liquid, we see that what ends up in the liquid is 60% nitrogen and 40% oxygen. And that is because the liquid has a much higher affinity for the oxygen than it does for the nitrogen. I want you to kind of think about this a little bit because we'll come back to it when we talk about wort and wort aeration. Let's jump back into oxygen sensors a little bit and talk about the different types. So there are two main types of oxygen sensors. There are electrochemical sensors and there are optical sensors. Electrochemical sensors have been around in the brewing industry since the late 70s, and they're kind of the classic membrane-covered Clark-type polarographic probes where you apply a voltage to an electrode, and from that voltage you measure a current, which is proportional to the oxygen content. When we talk about optical sensors, we're talking about an optical principle where O2 quenches the fluorescent activity of a polymer matrix. So we've got a polymer matrix. The oxygen permeates into the polymer. We hit that polymer with a blue light that excites the fluorescent material, and we get a red response back to the sensor. So essentially what we're doing is we're flashing light into the fluorescent material to make it fluoresce. The O2 quenches that fluorescence, and we'll measure the response back on a detector. What's going on in this slide is that we're looking a little bit and diving a little deeper into the optical sensor. So with the optical sensor, you excite the fluorescent material with a blue light, and then you get a red response back. If you take a red light and flash it onto the optical, you get back a reflection that gives you a good idea of how much of a drift you've had of the sensor. So you can kind of predict drift. You can look at the phase shifts between the red light and the blue light responses, and they're inherently much, much more stable than electrochemical probes. They're also more stable when you have line stops and starts. So if we look at the graph on the left, rather the graph on the right, what you'll see is as a line starts and stops with an electrochemical probe, the probe consumes the oxygen, and you'll see the dips in that response. On the top, what you see is you see an optical probe sitting in the liquid stream, but because the oxygen is not consumed by the sensor, the measurement stays very stable. Electrochemical sensors have some advantages over optical sensors, although they are much harder to maintain, and they do have downward drift, which has some complications. They have an incredibly high dynamic range. One sensor can go from 0 to 200 ppm with just a couple of parts per billion of uncertainty on the low end and maybe 1% on the high end. It makes them really great for wort and beer. But the cons are that the instruments require warm-up time. The downward drift can lull you into a sense false of security. They have complicated maintenance, which has to be done much more frequently than maintenance on an optical sensor. The pros of an optical sensor are that they have a great fast response time. Low drift, minimal maintenance. You use less beer because if you don't remember when you turned it on, or you forget and walk out to your tank and turn it on and then you walk away, you're not running a lot of beer to the floor. The cons are that you have to have probes that are tuned for different dynamic ranges. So typical low probe is going to be about 1 part per billion up to 2 parts per million, and a wort probe is going to have a dynamic range of, say, 0.1 part per million to maybe 30 or higher parts per million. The only con with them in terms of CIP interference is that chlorinated products, peracetic acid, and a few other things can react and quench the fluorescent material. But if you turn the sensors off and you're careful doing your CIP, it shouldn't be any interference problems overall. Okay, let's shift gears now, and let's talk about wort O2 measurements. So why measure wort O2? Really, it comes down to yeast health. If you give yeast too little O2, they don't have enough oxygen to reproduce initially, and it will stall your fermentation. If you give yeast too much oxygen, you'll end up with too hot a fermentation, and really what the bottom line is that the yeast is using fermentable sugar from the malt. They're also consuming some of the amino acids that are in the wort. And it seems like this amino acid consumption really requires optimal oxygenation. If it's too high or too low, the yeast consume the amino acids in the wrong sequence, and by doing that can create a lot of unwanted off flavors and a lot of unwanted problems. So where do we want to measure? We want to measure as far as possible from injection points. So we want to give that gas, whether you're using air or oxygen, as much possible time to dissolve into the liquid. Whether you have an inline probe or a portable probe, you also want to measure before yeast addition. So measuring the beer as close to the tank as possible is going to give you your most accurate measurement. oxygen in the form of air loves to migrate into beer. It can do it anywhere where you can create any kind of a Venturi effect through pumps, valves, filters, centrifuges, essentially anywhere that you could have an air leak. So as the liquid goes through the pipe, the air gets sucked into the liquid. Fermentation vessels have low O2 residual. So typically what you might want to do is get a baseline value at a fermentation vessel, measure after pumps, after filters, measure in bright beer tanks, and look at the effects of filtering and the filtration process from the fermentation vessel to the bright beer tank. Along the way, you could have dosing tanks that cause problems. You could have residual air in fermentation vessels, or you could have O2 that's in the filter before you start pushing the beer. You can also use these analyzers to measure the base of the filler after you push the beer from the beer tank to packaging to get an idea of what's going on before you put the beer in the package. I want to switch gears here and talk about package air. So package air is the gas that you get out of a container when you release the headspace gas through caustic. The caustic consumes the CO2, and you end up with a bubble at the top of a burette, and you call that air. If you look at that air in terms of headspace air from a package, it would follow Dalton's law. And if you look at it in terms of liquid air, it would follow Henry's law. So when we move on to this next slide, I want you to keep that in mind. You've got 80-20 ratio and the 60-40. So if we look at the bubble and we say we have a quantity of air and it all came from the headspace. So we had a package where we packaged perfectly. We got bubbles of air out of just the headspace. They would follow the blue line. They would show you what's in the headspace. And the air measurement can correlate fairly well to headspace air if you do a really good job and follow the ASBC method. The upper line, though, is what you would get if everything was in the liquid. If all that bubble of air was dissolved into the liquid, or what of it would dissolve into the liquid is dissolved in the liquid, then we would get the upper line. And you can see they're completely different. And since that resulting bubble is an unknown O2 ratio between the headspace and the liquid, we end up with a value that really is hard to correlate back to any other kind of a measurement. I just wanted to go back and do a quick review of solubility of air in a liquid and just show the relative solubilities. So just to go back and correlate what was different about the magenta line in the previous gas, it was the 60% to 40% ratio of oxygen that dissolves in a liquid, and that would be why you would get that upper magenta line. The reason that I think it's important to measure package O2 is because you can really look at things and validate exactly what's happening. You can look at your O2 at the base of the filler. You can look at the O2 in an unshaken package after it's been filled. And these two values, if you take your unshaken dissolved oxygen minus what's at the base of the filler, you will get your filler pickup value. You can shake the packages too, and you can incorporate the headspace gas by shaking, and that really gives you the ability to calculate TPO from a dissolved measurement. So what is total package oxygen? Total package oxygen is all of the O2 that's in the liquid in the headspace. So it's the O2 trapped in the liquid that came from the bright beer tank that was picked up in the filler, and then the headspace O2 is the O2 that was in the foam after fobbing, after the closure goes on. So what we want to do is we want to look at the total O2 in the package, because ultimately all that oxygen is going to react with the beer. And if you give that beer enough time In fact, just in some cases of some types of packages, it's only days. There will be no O2 left in that package. So it's really important to look at the total package oxygen content of a beer. If we take that total package oxygen content and we compare it to air versus TPO, what we see is that you can have air contents with really, really different total package oxygen. So if we look at valve B, or really hone in here on valve B, what we see is that we had an order of magnitude higher total package oxygen from bottles off of one filler valve. So we had a filler valve, 10 samples, 800 parts per billion, versus the rest of the filler where we were getting numbers closer to 80 parts per billion. But look at the air content. It didn't really change. We had 0.25 in the 80 to 100 ppb packages and 0.35 in the 800 ppb package. So why measure TPO? It's a normalized value. You can use it regardless of whether you're measuring a 16-ounce, a 12-ounce, a 22-ounce, or a 750 package size. You can use it for statistical process control. The numbers are statistically significant, and you can really go back, troubleshoot fillers, look at where your O2 is getting into the system, and it's an incredibly valuable tool. So what affects TPO? The dissolved oxygen and the headspace oxygen. So if we know either the dissolved oxygen or the headspace O2, we know the headspace volume, the liquid volume, and the temperature, we can calculate the TPO of any package. Everywhere in the process that you pick up oxygen, the oxygen will have a cumulative effect on the beer. So it's really important to try and keep your oxygen levels as low as you can every time you move it, as it goes through filters, dosing into tanks. It's probably more important to look at the cumulative effects than it is to really focus on any one area, but obviously you want to look at troublesome areas and solve those problems first. If you want to use inline measurements, you can. They give continuous feedback, but that's not to say that a portable can't give you the same data. Oxygen control is really important for prolonging shelf stability, and I don't know of a better method than total package oxygen for quantifying O2 pickup and helping you troubleshoot fillers and areas of O2 ingress. Thank you for watching this quick WebEx